Welcome to AI Paperslop. Today we are looking at Flash-WAM, Modality-Aware Distillation for World Action Models.
Yeah, this is a really big one.
It is. And if you are an AI researcher or an ML engineer working on embodied AI, here is the quick summary of why you need to care.
Right.
World Action Models, or WAMs, like Lingbot VA, jointly generate video and robot actions using diffusion. But they require dozens of denoising steps. We're talking over 8 seconds per chunk, which just completely kills real-time robotics.
Oh, absolutely kills it.
Now, standard step distillation, like latent consistency models, or LCM, utterly fails here because video and action streams use fundamentally different noise schedules.
Right, the distributions just don't match up.
Exactly. The action gradients vanish quadratically, completely destroying the policy. But Flash-WAM fixes this with modality-aware consistency functions.
Which is such an elegant solution, honestly.
It really is. They give the action stream a linear scaling parameterization. The result is a massive 23x speedup. They compress generation down to one step to modality, cutting latency to 348 milliseconds.
Wow.
Yeah, meaning they achieve real-time humanoid robot control without losing the accuracy of the heavy model.
I mean, it is hard to overstate the stakes of this specific bottleneck. Solving inference latency is arguably the holy grail for embodied AI right now.
Oh, without a doubt.
We have these massive models that understand the physics of the world beautifully, but if they cannot think fast enough to act in the real physical world, they just remain stuck as, well, highly expensive lab experiment.
Right. And to understand why Flash-WAM is such a massive breakthrough for you, the engineer trying to actually deploy this on moving hardware, we really need to look at the architectural corner that modern WAMs have kind of painted themselves into.
Yeah, let's look at the broader shift in the field. For a long time, the dominant approach was vision language action policies, or VLAs.
Which were great for static visual understanding, right? You feed them a picture, they understand the scene.
Exactly, but VLAs struggle with novel physical dynamics. They don't have an intuitive grasp of how objects fall or bounce or, interact over time.
I just don't know the physics.
Right. So the field shifted to WAMs. WAMs learn how the physical world actually works through massive video pre-training. They inherit these deep spatiotemporal priors just from watching countless hours of video data.
But there is a massive catch with WAMs like Lingbot VA. They use a two-stage diffusion process.
Yes.
At each control step, the model first has to denoise a chunk of future video latents, that is the visual dynamics prediction. The model is literally hallucinating how the world is about to change.
Based on its current state, yeah.
Right. Then it runs a second process, the inverse dynamics, to recover the specific robot actions that would logically cause that visual change. And both of those stages require iterative, step-by-step denoising.
And the raw numbers on that denoising process are just, they are brutal.
Yeah, they really are.
Lingbot VA runs 25 video steps and 50 action steps, the 25V50A configuration. If you run that setup on an NVIDIA L40S GPU, it takes over 3,500 milliseconds just to figure out the video.
Just for the video part.
Right. And then another 4,500 milliseconds to calculate the actions. You add that up, and you are sitting at 8.1 seconds per chunk of movement.
Imagine trying to play ping pong, but your brain takes 8 seconds to process the visual of the ball and tell your paddle to swing.
You'd miss every single time.
Exactly. By the time you move, the game is completely over. Real-time control budgets are around 500 milliseconds. Taking 8.1 seconds to decide to move your arm is just an absolute eternity.
If we connect this to the bigger picture, engineers have been trying to hack their way around this latency for a while now.
Oh yeah, lots of workarounds.
If you look at the literature, you see attempts at using KV caching to store past observations or partial denoising with noisy history augmentation.
Right, trying to reuse old compute.
Exactly. Some teams even try setting up asynchronous pipelines where the robot acts while it's thinking, but those are fundamentally just band-aids.
It's like trying to make a 10-hour flight feel shorter by installing more comfortable seats in the airplane.
That's a great way to put it.
You aren't actually changing the speed of the engine.
Yeah.
Right? You are just trying to distract yourself from the weight.
Right. They reduce the wall clock latency slightly, but they do not change the underlying computational cost.
The sheer number of denoising steps required to get a clean output.
Exactly. To actually achieve real-time control, you have to compress the denoising math itself.
So if the number of denoising steps is the bottleneck, my first instinct as an engineer is to just, teach the model to skip them.
Naturally.
Why can't we just force the model to memorize the final output and jump straight there? Which brings us to the obvious solution that everyone reaches for, which is step distillation.
Specifically, consistency models. or latent consistency models, LCM. The core idea of step distillation is really elegant. In standard diffusion, you follow this winding step-by-step trajectory from pure random static down to a clean generated output.
Slowly carving away the noise.
Exactly. Consistency models enforce a rule where any point on that noisy trajectory maps directly to the final, clean endpoint in a single jump.
You're basically training a student model to draw a straight line from start to finish.
Right, completely bypassing all the intermediate calculations.
And it works beautifully for generating single images or standard video on the internet.
Oh, flawlessly.
So naturally, researchers took off-the-shelf LCM and applied it to the LIBERO VA, the Joint Video Action Model, but the results were catastrophic.
Yeah, catastrophic is the right word.
And I don't mean a slight dip in performance. When they applied naive joint LCM, the success rate on the RoboTwin benchmark just collapsed.
From what, 90%?
Normally, LIBERO VA hits over 91% success on these manipulation tasks.
Yeah.
With naive LCM distillation, it plummeted to a dismal 24%. The robot basically forgot how to do its job. So what actually broke here?
The technical diagnosis comes down to asymmetric noise schedules. Video latents and robot actions are just not the same type of data, and they have fundamentally different statistical properties.
Right, they aren't equivalent.
Think about video. It is incredibly high-dimensional and has a massive amount of structural redundancy. If your model gets a few pixels wrong in the background, it is still clearly a video of a kitchen.
Because of that redundancy, video models use a high signal-to-noise ratio shift.
Yes.
They can tolerate and actually require a lot of heavy noise during training to learn the broad structure of the world.
Precisely. But actions are the exact opposite. Action tokens, the raw commands telling the motors how much torque to apply, they are low-dimensional.
And precision critical.
Incredibly precision critical. If your robot gripper is off by just 2 centimeters, you don't just get a slightly blurry video frame, you completely miss the handle of the mug.
Or worse, you crush the object you're trying to pick up.
Exactly. So the action stream uses a uniform or low signal-to-noise ratio shift. It spends most of its training time focusing on fine, low noise adjustments because precision is everything.
Right.
And here is where the collision happens. Because video needs high noise and actions need low noise, these two streams reach the consistency distillation loss function with substantially different distributions of data.
The video data is heavily concentrated at the high noise levels.
Right. And the action data spreads across the full range, but places a massive amount of its training mass way down at the low noise levels.
Okay, let's unpack this. I get that they have different noise levels.
Yeah.
But in a model like LIBERO VA, the action and video streams are just concatenated tokens. They are passing through the exact same flow-matching transformer backbone. If the architecture is shared and they're being hit by the same consistency loss at the end, why does having a different noise schedule actually break the underlying math?
It's a great question.
Shouldn't the optimizers just, figure it out and balance the updates?
Yeah. You would think so, and honestly, that was the prevailing assumption for a long time. But it's a structural mathematical failure, not just a tunable inefficiency.
Okay, so how does the math actually fail?
To understand why the optimizer fails, we have to look at how consistency functions actually pass learning signals to the neural network. Without getting bogged down in the literal equations, any consistency function uses a scaling parameter.
Okay.
Think of it as a volume knob that controls the learning signal. It dictates how strongly the network is allowed to update its weights based on the errors it makes at different noise levels.
Okay, a volume knob for the learning signal. I like that.
Now, look at the specific volume knob used by standard latent consistency models. It is mathematically designed with a curve that flattens out completely at the bottom.
At the low noise end?
Yes. As the noise level gets close to zero, the derivative of that curve goes to zero, meaning the volume knob effectively turns itself off.
Oh, wow.
In fact, if you map it out, the learning signal shrinks quadratically as noise approaches zero.
And there is the trap. The action stream uniform noise schedule forces it to put a ton of its training data down in that low noise regime, exactly where precision matters most.
Exactly.
But it's operating exactly where LCM's volume knob has turned the learning signal off.
It is completely starved of learning signal. To give you a concrete comparison, at a noise level of 0.1, standard LCM's gradient scale factor is roughly 36 times smaller than what it is up in the high noise regime where the video stream lives.
36 times smaller.
Yeah. The video stream is sitting in the high noise area, getting a massive, healthy learning signal so it learns to distill perfectly.
And the action stream gets nothing.
Practically nothing. It's like trying to teach two students in the same classroom, but for one of them, the teacher's microphone is muted.
So the video learns, the actions are starved, and the robot's policy collapses to that 24% success rate.
Right.
I have to ask, though, if the math so clearly zeroes out at low noise levels, why did no one notice this before? I mean, we've been using LCM for a while now. Did people just assume multimodal models would magically balance themselves out?
In a word, yes. In single modality generation, like just making a video or just making an image, the entire model operates on a single noise schedule that perfectly matches the LCM parameterization.
Ah, I see.
The problem only rears its head when you try to force two completely different modalities with two different noise schedules through a single distillation loss. We basically abstracted away the statistical properties of the data once it became a token and assumed the transformer would just handle it.
That is a fascinating diagnosis. And once you prove mathematically that standard LCM inherently starves the action stream because of that quadratic vanishing, the solution suddenly becomes glaringly obvious.
Yeah, it points right to the fix.
You cannot use the same math for both modalities. You need modality-aware consistency functions, which is exactly where Flash-WAM steps in.
Flash-WAM approaches this by treating video and action distillation as fundamentally different mathematical problems requiring distinct learning signals.
Right.
For the action stream, they completely ditch the LCM parameterization. Instead, they use a simple linear scaling parameterization. They make the scaling parameter directly proportional to the noise itself.
So instead of a complex curve that flattens out, it's just a straight line.
Exactly. It is a profoundly simple fix. By using a linear parameter as the noise drops towards zero, the learning signal shrinks linearly, not quadratically.
Okay, so it doesn't vanish.
Right, it doesn't vanish. It just smoothly powers down, leaving more than enough signal for the network to keep updating its weights. You completely bypass the trap.
So the action stream finally gets a strong, consistent learning signal exactly where its training data actually lives.
Yes, the action policy is totally rescued.
Now, I can hear the ML engineers listening right now thinking, wait, if the linear function is so great and completely fixes the vanishing gradient, why not just use that straight line for the video stream too?
It's a fair question.
Right. Why make the system complicated by running two completely different consistency functions?
Because solving one problem creates another if you don't respect the data. This raises an important point about stability in high noise regimes.
Okay.
Remember, video lives way up in the high noise end of the schedule. If you use that simple linear function up there, you run into massive problems with variance preservation.
What does variance preservation actually look like in practice here?
Think of it like turning the steering wheel of a car. The standard LCM parameterization is designed to keep the variance of the function stable. It inherently caps the output magnitude.
Like a limit on how far the wheel can turn.
Right. It's like having a governor on the steering wheel when you are driving 100 miles an hour. If you make a tiny mistake at high speeds or high noise, the math prevents that error from multiplying and spinning you off the road.
But the linear function doesn't have that governor.
Exactly. If you use the linear function at high noise, the variance grows directly with the noise. A tiny prediction error by the network gets mathematically multiplied by a massive noise factor.
Oh, yikes.
Yeah. Suddenly your steering wheel jerks hard at 100 miles an hour, and your generated video latent is completely blown out. The model drifts right off the data manifold.
So for low-dimensional bounded robot actions living in low noise, that drift doesn't matter. The linear function is perfect.
Exactly.
But for high-dimensional video latents at high noise, it will absolutely destroy your image quality. Therefore, Flash-WAM deliberately keeps the standard LCM parameterization with its built-in boundaries for the video stream.
It essentially respects what each modality physically needs to remain stable and continue learning.
Here's where it gets really interesting for me. We're talking about two completely different consistency targets, using different parameterizations and different math. As an engineer, your first thought is that this requires some heavy bloated new architecture.
Yeah.
You picture split pathways, complex routing, and a total nightmare scenario for serving this model in production.
Oh, sure.
But it doesn't. Both of these consistency targets are computed from a single forward pass of the shared transformer.
That is the architectural beauty of Flash-WAM. It costs absolutely nothing extra in terms of compute.
And nothing extra at all.
You still concatenate the video and action tokens, and you pass them through the exact same shared transformer with flex attention, just like the original slow teacher model. The modality-aware parameterization only changes the math at the loss heads during training.
Right.
At inference time, your deployed architecture is literally identical to the baseline. It is just operating vastly fewer times. This is a structural realization about how we parameterize gradients during training, not an architectural hack you have to maintain in production.
Okay, the math makes total sense. The diagnosis of the vanishing gradient is incredibly clean. But for you, the engineer trying to ship a real product, theoretical elegance doesn't really move the needle.
No, it has to actually work.
The only thing that matters is whether this works on physical hardware in a chaotic environment. Let's look at the empirical wins, starting with the simulation results. They took that sluggish 25v50A Lingbot VA model and Flash-WAM compressed it down to just 1v1A.
One step.
One single step to generate the video, one single step for the action.
And the latency drop is just staggering. It goes from that agonizing 8.1 seconds down to 348 milliseconds.
That is a 23.3x speedup.
Yeah, they safely cleared that 500 millisecond real-time budget for hardware control.
More importantly, the success rates did not collapse like they did with naive LCM. On the RoboTwin 2.0 simulation, the massive slow teacher model was sitting at a 91.2% success rate. Flash-WAM, operating at just 1v1A, held on to an 81.4% success rate.
Which is an incredibly acceptable trade-off for a 23x speedup.
Totally. And on the LIBERO benchmark, it was even better. A 95.1% success rate with just one single step.
But simulation is always clean, right?
Right.
The real test is the physical hardware, the Unitree G1 humanoid robot experiments. Real-world robotics is where the noisy physics of the actual environment usually breaks fragile, over-distilled models.
Yep, the real world is messy.
The team tested the Unitree G1 on 3 specific manipulation tasks. Opening a pot to put a potato inside, picking up a red bottle while ignoring a brightly colored yellow distractor, and picking up a pink object to place it precisely on a target.
I always love how beautifully mundane robot benchmarks are. Put the potato in the pot.
Right.
But the continuous spatial control required to not drop the potato or knock over the pot is just immense.
It is incredibly difficult for a machine. The unaccelerated slow teacher model achieved a 66.7% average success rate across those physical tasks.
Right.
When they deployed Flash-WAM running at 1v2A, so one video step, 2 action steps, it achieved a 60% success rate.
That's practically identical.
And when you watch the footage, the robot successfully pops the potato into the pot really fluidly. It isn't pausing for 8 seconds like a frozen video game character buffering its next move.
Buffering, yeah.
It retains almost all of the teacher's physical capability while moving in real time.
Now contrast that fluid movement with the baselines. If you try to just use the undistilled Lingbot model, but force it to run faster by arbitrarily cutting the denoising step short, the success rate plummets to 40%.
It just starts flailing.
Literally flailing. If you use a video-only LCM approach, where you successfully distill the video stream but leave the action stream alone, it still falls to 43.3%.
What's fascinating here is the visual reality of why naive LCM fails. The authors provided a qualitative detail from an open-loop rollout that paints a really clear picture.
Oh, I love this part.
Right, so in an open-loop rollout, the model has to generate all subsequent video chunks based entirely on its own past predictions without any new observation feedback from the cameras to correct it.
It's flying blind on its own imagination.
Yeah, exactly. With the naive LCM baseline, the model literally loses track of a brown bottle sitting on the table. Over a few frames, it just vanishes like a ghost.
Because the model's internal physics engine, its visual dynamics, completely degraded under the wrong distillation math. It literally forgot the bottle existed.
Yes.
But with Flash-WAM, the object identities are preserved perfectly across the entire continuous rollout. The brown bottle stays exactly where it should be, solid and present.
And the ablation studies confirm that you can't cheat this math. You might be listening to this and thinking, okay, naive LCM breaks the actions because the gradient vanishes. What if we just distill the video properly with LCM and slap a simple mean squared error flow matching regularizer on the action stream to keep it stable?
Yeah, just hack a fix onto it.
Right, but the ablations prove that shortcut does not work. When your inference budget is this tight, distilling the action stream properly with its own matched consistency function is absolutely mandatory.
You cannot fake it with a generic auxiliary loss.
No, it requires targeted modality-aware math.
So what is the ultimate takeaway for you, the person actually building these systems? If you are engineering multimodal diffusion systems, treating all your modalities uniformly during distillation, is a trap.
A massive trap.
You cannot just take a hammer like LCM and hit every part of your architecture with it. You have to respect the marginal noise distributions of your specific data types.
Action data is fundamentally not video data.
Exactly. It requires precision, it trains at different noise levels, and if you ignore that physical reality, the math will quietly mute the microphone and starve your network of learning signals.
It is a profound lesson in the mechanics of multimodal machine learning. As a field, we often abstract away the statistical properties of our data once it becomes a uniform token in a transformer.
Right, we think a token is a token.
A token is a token, right. But during diffusion distillation, those underlying statistical properties actually dictate the physics of the learning gradient.
Which brings me to a final, forward-looking thought for you to chew on as you go back to your own models. Flash-WAM clearly proves that tying specific mathematical parameterizations to specific modality noise profiles unlocks 23x speedups for video and action.
Yeah.
But what happens when we scale this up to truly universal foundation models? Imagine a few years from now, we're integrating high-frequency tactile feedback from a robot's synthetic fingertips.
Oh, wow.
Plus raw continuous audio processing from the room's environment and continuous semantic language reasoning, all injected into the exact same diffusion backbone.
I mean, every single one of those modalities will have its own distinct dimensionality, its own structural redundancy, and its own unique marginal noise distribution.
Exactly. Will we need 5, 6, or 7 entirely different consistency functions operating simultaneously just to keep the gradients alive across the network?
That is a wild thought.
And if we can successfully map those functions out, could this modality-aware math be the final missing key? Could it be the thing that takes massive, slow, human-level cognition models and compresses them down to run on cheap, edged compute robot brains in real time?
It completely changes how we think about scaling embodied AI. It's not just about bigger GPUs anymore. It suggests the future of these foundation models isn't just about scaling up brute force compute. It's about deep, elegant mathematical alignment between the loss function and the physical nature of the data itself.
Well said. That is all the time we have for today. Thank you for joining us on this deep dive into the paper, and we will catch you next time on AI Paper Slop.